In this video, we're going to continue our discussion of sketching graphs on a very basic level, which, as I kind of mentioned in the last video, we wrote a few things down, was kind of like a four-step process, which basically involved probably maybe isolating a variable in your equation. You're going to notice here I've already got a function written out here that, for the sake of convenience, and I want to prove a point later with this function. But basically, isolating y and then maybe creating a table of values. And again, I know I'm talking to probably people who are in calculus pre-calc. I can't stress enough how convenient this is. Not convenient is, but people tend not to do the basic things, and they maybe make mistakes because of this fact. So we'll go ahead and make a table of values here and maybe take a look at sketching this graph. But again, just basic stuff. Let's say we plug in -2 here, okay? So we'd have essentially y equals, and another good habit again is put in those parentheses wherever you're plugging in for. But our input value is -2, and in this case we have -2 squared, which is +4 minus 2 is 2. So working back, we say, what if we had -1? -1 squared would be 1. 1 minus 2 is -1. And so I'm going kind of quick here. 0 squared minus 2 would be -2. And of course, if you're already familiar, this is a parabola with a positive leading coefficient, so it's going to open up, and we say, okay, it's going to demonstrate a certain level of not symmetry in this case, but kind of what I'm going to be getting at here. But we say, okay, let's go ahead and take a look at this here. So we said we had -2, 2. Once you get your table of values made, of course, we said let's go ahead and plug them in and see what this puppy looks like here. Say, okay, so 1, -1. Oh, I was wondering why that looked off. So we say, okay, so -1, comma -1. Here we say, okay, so 0, -2, 1, comma 1, and 2, comma 2. Okay, so here's our parabola right here, and we could label these points, but we say, okay, so we got this basic method down. I mean, it's great and everything, but here's a few things I want you to notice. When we come to sketching graphs sometimes, we're going to come across some things that are going to have not maybe second degree equations, but maybe like a fourth degree or fifth degree equation, or that is the highest power on a variable is going to be of a high degree. And so the graph may be irregular. And again, if we have these points written out, we can sketch in the graph and some basic knowledge. But what I want to do is I want to basically posit one argument here. What if we knew, okay, say maybe these 4 points were on the graph here. These 4 points, and we'll go back to basically, maybe we assume we didn't know this point was on the graph. All we knew were these 4 points. What I want you to know is this. If we had some irregular equation, who is to say that it maybe doesn't look like that? Okay, we have maybe a set of hyperbolas, or in another instance, we may even have a circle. So what if we had, basically a circle passing through these, or even better, how about, I don't know if that's much of a different color pink. We'll try and switch it over again to green here. What if we even, had our parabola that we do have here? Sorry. They would all proceed through these points is what I want to get at here, these 4 points. So the point I'm trying to make here is this. Necessarily making a table is not enough to give us all the information that we might want to know when sketching a graph. So here's the thing about it. We're going to look at 2 other essential facets of pretty much every graph or variable relationship, but these are what we call intercepts, okay, intercepts and symmetry, okay. Just kind of talking about this, we said intercepts. What are intercepts? Well, essentially what we would be doing is solving for solution pairs by plugging in, some given x or y values, specific x or y values, in which maybe our graph say strikes the y-axis. So we would consider this here maybe like a y-intercept, or we may have a polynomial that proceeds like this. And in this graph here, we say it has multiple intercepts. It has these x-intercepts right here, and it has a y-intercept right here, and I suppose I could be drawing these in different colors. But the fact of the matter is this. It would be very helpful to know where the intercepts are, okay? And in the next video, we'll talk a little bit more about how we might use symmetry, or at least check for it. Because let's say we knew where our graph, say, hit the x and y axes, that would give us kind of, kind of let us infer about the graph. Kind of like this one over here hit the y-axis at this spot here, which would allow us to kind of rule out that it's not a hyperbola, or, it wasn't necessarily a circle, okay? But we say, okay, intercepts are helpful in finding where it crosses these boundary points, okay? And symmetry would be helpful if we, say, knew half of a graph that came down and we could tell somehow that it was symmetrical about the y just by looking at its rule. We could say then we would necessarily know the other half of the graph. But again, in this video, let's go ahead and proceed to talk about intercepts more than symmetry. Okay, so I'm going to switch over to kind of say a light blue here, but let's go ahead and take a look at these points right here. Algebraically and geometrically, you're going to notice that this is some point on the y-axis. And the convenient thing about intercepts is that we can basically deduce already one of these two coordinates in the coordinate pair. And in this instance, we can say that we know whatever this point here is, it has some height y, but we can at least say that it has an x value of 0. And for any say x-intercept, we know that this has some given x value, but we know at least a y value of 0. And the reason why that's so convenient is because going back to say our original example here, we say y equals say x squared minus 2. We could check to see if this had any intercepts, and we would do so simply by using the fact that we know that y is 0 when we have an x-intercept, and x is 0 when we have a y-intercept, and that's an if and only if. So using that fact, what we can do here is we can go ahead and flip open a new screen here so we have a little bit more room. Go ahead, zoom in on that, and why not go back to black. So checking for intercepts, I just wanted to go ahead and write this down real quick, and that's all. Nothing too big, but how we might do so. So we say checking or intercepts. Okay. So we say in order to check for an x-intercept, we say, okay, insert, or y-intercept, insert the value 0 for x or y, okay, and then simply put, we say solve for the unknown variable that's left over, okay? And essentially what we're finding is that variable's intercept. So what if we go back to that example like we mentioned, y equals x squared minus 2. We knew what this looked like, okay? And knowing what that looked like is going to help us in this example. Let's say we wanted to find, say, the x-intercept. The interesting thing about finding the x-intercept, okay, or where our graph strikes the x-axis, is we necessarily want to plug in 0 for y. Again, if it's hitting the x-axis, we know that every point on the x-axis has a y value of 0. So we say, okay, so to find the x-intercept, let's plug in 0 for y. So we say x-intercept, plugging in 0 for y. So we say x-intercept here. That's an n, sorry. But we say, okay, so let's go ahead and solve for x. So we say adding 2 to both sides. I mean, simple algebra. We say, okay, so x squared is equal to 2. And therefore, we say square root of both sides. X is equal to not just square root of 2, but plus or minus. Okay, so going back to that last example, we said we had, -1, -1, and 1, 1. And we say here, okay, so we had 0, -2. And we say if we were to cast this graph across here, we say, okay, so it hits the x-axis at an x value of negative square root of 2, comma, 0. There's that 0. And we say, okay, and it hits the x-axis at positive square root of 2, comma, 0. And to solve for this y-intercept, algebraically, we say, okay, to find a y-intercept, the method is simply, we'll plug in 0 for x. We say y would have been equal to, now, 0 squared minus 2. So y, simply put, is just -2. And so it always happens to be the case, by the way, if you have y isolated in an equation that, well, not always the case, I shouldn't say that, but with a polynomial, this constant value, c, we say is the y-intercept. But we say, okay, so we got this point here. 0 was plugged in for x, and -2 is our y. So again, the whole point of searching for our intercepts is to kind of give us just a little bit more of a hint about how our graph behaves, or at least where it goes through. And it's a nice thing to check for intercepts because sometimes there is no intercept, and you're dealing with something that may be like, say, for example, asymptotic, has an asymptote, like an exponential equation, or it's nice to plug in zeros anytime you get a chance. So Checking for intercepts is going to be one of our big things, and in the next video we're going to discuss this idea of symmetry. Why would we want? Why check for symmetry? Why?